Namaste and a very good morning to all of you. My name is Mithun. In today's video, I'll be talking about linear regression. How do we perform linear regression model using Python? Before I show you how to execute a linear regression model, may I request you to subscribe to my channel and like and share my videos. Firstly, what exactly do we mean by linear regression model? Linear regression model is a supervised machine learning technique. In this technique, we have a dependent variable and an independent variable, or we may have multiple independent variables. Linear regression technique is the foundation of many multivariate analytical techniques. So in this example, I will be showing you step-by-step procedure as to how we can execute a linear regression model. Let's begin with elementary codes. The first thing that I would do is to load the data set. Let me begin by loading the data set. The data set that I will be working on is a data set which is called as the Boston housing data set. This particular data set comes in with sklearn or scikit-learn library. Once you load the data set, the next step would be to display the feature names in this particular data set. So I will be using the command boston.feature names. You can see here, Python displays all the features that are present in this particular data set. Some of the features are crime rate, ZN, Indus, presence of Charles River, nitric oxide concentration, number of rooms, age, so on and so forth. Next, I would like to explore the data set in depth. So to explore the data set in depth, what I'll be doing is I will be using the command describe. As you can see here, Python describes the data set. It gives me the name of the data set as Boston house prices data set. The number of instances in this particular data set is 506. There are 13 numeric variables. We also have house price, which will be acting as the target variable. We have already gone through some of these variables. You can see a short description of some of these variables. For example, when we say crime, what exactly do we mean? It means per capita crime rate by town. Secondly, when we look at the variable NOx, what is this NOx? NOx represents nitric oxides concentration, which is measured in parts per 10 million. RM, this is the average number of rooms per dwelling. Let me scroll down. When I scroll down, you can see an empty cell. In this particular empty cell, we will be writing additional codes to explore the data set. Before I explore the data set, there's a very important step that I'd like to do. What is this step? I'd like to convert the original array data into a data frame and append the column names. Now, a data frame is like a spreadsheet. It gives us a spreadsheet-like view, and therefore it is very easy for us to comprehend and work with a data frame. So let me convert this original array data into a data frame. You can see here, this is the command that I'll be giving, pd.dataFrame. And in the third line, you can see we will be displaying the contents of this particular file. This is how the data set looks like. We have all the variables in this particular data set. And when we give the head function, it will display the top 5 rows that are present in this particular data set. Moving on, what is the next step after this? We would like to add the dependent variable in this particular data set. The dependent variable is housing price. So let me go ahead and execute the housing price. You have the list of variables, and as I scroll to the extreme right side, the last variable that you see is the housing price. So housing price is the variable which I will be using as the dependent variable to build a regression model. The rest of the variables will be acting as the independent variable. Let's keep this discussion going. I would like to summarize the data set. To summarize the data set, we have a very, very useful function, which is called as the describe function. So let me go ahead and use the describe function. You can see here, describe function reports many useful statistics like count, mean, standard deviation, minimum, so on and so forth. If you look at the average crime rate, it is 3.6%. Similarly, if you look at the average nitric oxide concentration, it is 0.55 units. On an average, the number of rooms would be 6 rooms. This is how we can interpret the statistics for each and every variable in the data set. Now that we have described the data set, what is the next step? The next step would be to generate a correlation matrix. I repeat, the next step would be to generate a correlation matrix. We'll be using a very simple function, core function, to generate a correlation matrix. As you can see here, for all the variables, you see correlation values being displayed. Some of these values are negative, others are positive. Now, when you have so many numbers, it becomes a bit difficult to comprehend which of them have a strong relationship, which of them have a weak relationship. This is where heat map comes to our rescue, because using a heat map, we can clearly tell which of these variables have a strong relationship with its neighboring variables and which of these variables have a weak relationship. I'll have to use the Seaborn package. Let me quickly use a heat map function. Let me go ahead and generate the heat map for the correlation values. You can see here, this is how the heat map looks like. You can see here the color scaling to the right side. All the high values, if the values more than 0.7, it is depicted using the green color. And if the value is less than minus 0.7, it is shown using the red color. So strong negative correlation is highlighted using red color, and strong positive relationship is highlighted using green color. If the correlation is weak, it appears as, if the correlation is moderate, it is shown in terms of yellow color. You can see the last variable here, housing price, which is the dependent variable. There are certain variables like crime rate, index variable, nitric oxide concentration, which have a weak negative relationship with the dependent variable. There are a couple of variables. In fact, there's only one variable which has a strong relationship, which is the number of rooms present in the house. So you can see here the correlation value is 0.7, which means that as the number of rooms increase, the housing price also goes up, which makes sense because larger homes with a lot of rooms tend to command higher price. Now, you can see amongst the independent variables, a lot of high correlation values are present, indicating that there could be the problem of multicollinearity. We need to be very careful with the problem of multicollinearity, because if in the data set there is multicollinearity, it leads to overfitting issue. Let me scroll down. Now, I will be using the stats models library to build a linear regression model. Let me import the stats models to build the linear regression model. What next? The next step would be to fit a linear regression model. You can see here smf.ols. OLS stands for ordinary least squares. I'm just using the dependent variable and using the tilde function, and all the independent variables are listed here. Finally, I'm going to use the fit function to fit a linear regression model for this particular data set. We are not getting any error, which is a good sign because this indicates that our code has run successfully. What is the next step? The next step would be to see the output of this particular model. How do we do that? Just use the summary function. Model.summary should print the output. You can see here very quickly, Python displays all the useful statistics. You have useful information like what is the dependent variable, the name of the model, the method that we are using, and date time description. But I would like to draw your attention to what is called as R square. In this case, the R square is 0.74. R square stands for coefficient of determination. I repeat, R square stands for coefficient of determination. The value lies between 0 and 1. If the value is close to 1, it means that the model fits the data well. On the other hand, if the R squared value is close to 0, it means that the model does not fit the data well. Here, we are getting a R square value of 74%, which means that 74% of the variation in the housing price can be explained by the set of independent variables that we have taken. We can also see the F statistic and the probability of F statistic, which is less than 0.05. Further, against each independent variable, you can see crime rate, ZN, Indus, CHAS, we are shown the coefficient value. We also have the p-value listed. Those variables which have a p-value less than 0.05 are significant, and we have to consider them in the model. And those variables which have a p-value bigger than 0.05 are insignificant. For example, if you look at the variable Indus, this has a p-value of 0.73, which is clearly bigger than 0.05, and hence Indus variable is insignificant. We can go ahead and drop this particular variable in the next step. Similarly, I can see the p-value is reported as 0.95 for the variable age, and hence the variable age is also insignificant. Let's look at the unstandardized coefficient for NOx, nitric oxide concentration. The unstandardized coefficient that is reported is -17, which means if the nitric oxide concentration goes up by 1 unit, housing price comes down by $17,000. I repeat, if the nitric oxide concentration goes up by 1 unit, then the housing price goes down by $17,000. Similarly, based on the sign and the magnitude, we can interpret the coefficient for each and every independent variable. One other thing which is very, very important here is the Durbin Watson statistic. Durbin Watson statistic is a measure of autocorrelation. It tells us whether there is autocorrelation in the data set or not. Ideally, if there is no autocorrelation in the data set, the Durbin Watson statistic must be 2. I repeat, if there is no autocorrelation, the Durbin Watson statistic must be 2. If the Durbin Watson statistic is either less than 2 or greater than 2, it is an indication that there is a problem of autocorrelation in our data set. For example, here I'm getting the Durbin Watson statistic as 1.0, which is clearly less than 2, indicating that there is negative autocorrelation in the data set. Second point which I'd like to draw your attention to is conditional number. Conditional number speaks about multi-collinearity problem. Usually, if we have a very, very high conditional number exceeding 13, my apologies, if the conditional number value is greater than 30, it is a indication that there is strong multi-collinearity in our data set, which was quite evident because if you recall the discussion that we had in our heat map, there are a lot of variables which show strong relationship with their fellow independent variables. So whenever you have high correlation between independent variables, that's a clear indication that there is a problem of multi-collinearity. Now, when I scroll down, you can look at conditional number. This is a singular value. This single value itself confirms that there is high collinearity problem, multicollinearity problem in this data set. You can see the notes here, particularly the second point here. The condition number is large. This might indicate that there are strong multicollinearity or other numerical problems. I will not be talking about how to address the problem of multicollinearity in this video. Maybe another video separately I will make on addressing the problem of multicollinearity. Let's go ahead with the discussion now. Let us drop some of the insignificant variables. We already saw that we had two insignificant variables. If you recall, the variable indus has a p-value of 0.73 greater than 0.05, and hence we need to drop this variable. Similarly, the variable age, which has a p-value of 0.95, needs to be dropped from the model. Let me scroll down. I'll be building the model once again, but this time I will be dropping the two variables, namely age and indus. Let me go ahead and rerun the model. R square has not changed dramatically. Earlier I got a R square value of 0.74. Now again, after dropping these two variables, my R square has remained intact, which is a good sign. You can see here, now for each and every variable, the p-value is less than 0.05. Durbin Watson statistic, as earlier, is not very satisfactory. We are again being shown that the conditional number is large. We have not taken any action to address the problem of high conditional number in this particular example. Finally, since we are worried about Durbin Watson statistic or the autocorrelation problem, what we will be doing is we will be running a robust regression model. We will be printing heteroscedasticity robust regression, robust standard errors. So let me go ahead and execute this particular model. Now look at the output. We are getting by and large the same statistics. Now, one change here is standard errors are heteroscedasticity robust. This is the message that we are getting. Let's go ahead. Let's go back and look at the earlier output. The earlier output said standard errors assume that the covariance matrix of the errors is correctly specified. So we had a bit of a problem with the earlier output. Now we have been able to rectify this by building a robust regression model. So to summarize the discussion that we have had at this stage, we have built a linear regression model. We have looked at the coefficients. We have looked at the p-value. We have also looked at how we can interpret the R square. And very importantly, we have checked the Durbin Watson statistic. With this, I have come to the end of this particular discussion. I request you to subscribe to my channel and also press the like button. Thank you very much for watching this video. Have a great day.